Hello again. So last time we were talking about subspaces, and usually a good way to arrive at a subspace, as we'll find, is through the span of a set of vectors. So if we have, say, a1 v1 plus a2 v2 up to am vm for some set A in F. We call this obviously a linear combination or a sum of vectors. So nothing new there. Here's where we come to the next important part, and that is a span of a set of vectors in our vector space is the set of all vectors that are linear combinations of that set. And we write this as the span of the set v1, v2 up to vm. Okay, so a quick example. Suppose we had two vectors in R3, 1, 1, 0, and v2 is equal to 0, 1, 0. So our vector space, as I've mentioned, is R3, and the associated field is R. So given that all linear combinations I'll keep it in gray because it's the same example here. Of v1 and v2 can be written as a 1, 1, 0 plus b 0, 1, 0, which is going to be equal to, and I'm going to change the notation here, you'll see why, just to make things simple, this. For any x1 and x2 in R. In other words, it's plain to see that we can never reach the bottom third element in that row, and that's always going to be 0. And so in this case, we actually, it's easy to see that we have a subspace of R3, and it's the subspace that's spanned by the first two elements in our vectors. Okay, so once we have the concept of linear combinations, the next thing that comes up is linear dependence, or independence, depending on your view of things. Sometimes I do consulting work involving patent litigation, and they ask me to evaluate whether or not some product is infringing on a patent. And I find it very interesting, but it depends on which side I'm working for, whether they ask me to write an infringement report or a non-infringement report. And it's the same thing here. We talk about things being linear conditions for linear independence or linear dependence, depending on our point of view, but it's the two sides of the same coin. So really I'm just talking while I write, because I can't write quite quickly enough. But one beautiful thing about doing the video lectures is you can always speed it up and watch at a faster speed, and maybe that's easier. Okay, so linear dependence. A set of vectors, the set is called linear dependent if for some set of A where not all ANs are 0, you can sum up the vectors in such a way that they cancel each other and get you to 0. Okay. Of course, if they're all 0, then it's going to be equal 0. But they're linearly dependent if and only if there are some non-zero set of A's such that the linear combination of all vectors gives you 0. Okay, the flip side of that is, of course, linear independence. And for linear independence, the sum of all of our vectors equals 0 only for a n equals 0 for all n. Okay, so it's just the opposite. So let's go through one quick example. You've seen this before, but it never hurts to see it again and remember what all this was about. So assume, once again, we'll go to R3 because it's easy to visualize. We have V1 is equal to 2, 1, 0. V2, 1, 1, 0. And V3. Okay, so those ones appear to be linearly independent. But now we complete the set with V3, and it's linearly dependent. So why is it linearly dependent? Well, there are a lot of ways to go. One is you can find A1, A2, and A3 such that A1 V1 plus A2 V2 plus A3 V3 is equal to 0. There's a shortcut way of looking at this, and that is I've got 3 vectors spanning 2 non-zero dimensions. So we know that we have to have some linear dependence there. So any two of these are actually going to be linearly independent, but the three of them together are not. So and since they're linearly independent, we're actually going to get that the span of V1, V2 is equal to the span of V2, V3, span V1, V3, like so. So if you go to the actually, let me just go through one more example and one demonstration. Once again, I'm expecting this as review, and if it's not, if you follow the link on the top of the Canvas page to Mark Davenport's website, he has a link to a variety of resources, some of which are online, that are good reviews for linear algebra. Okay, so in example 2, pardon me for a moment. Yeah, let's do this one. So here we say S is equal to C 0, 1. We define, so it's continuous signals over the interval 0, 1. V1 is equal to cosine 2 pi t, and this is a function of t. V2 is equal to sine 2 pi t, and V3 is equal to 2 cosine 2 pi t plus pi over 3. So can we find a set A1, A2, and A3 such that the linear combination here goes to 0? And I'm going to leave this as an example for you to work on. But it turns out that yes, it can be done. And one way to intuitively view this is that they're all the same frequency, the frequency of 2 pi radians per second, or 1 hertz. And so what's different is the phase. If we just had a single term, say V1, we wouldn't have access, we couldn't switch the phase. But since we have access to V2, something that's 90 degrees out of phase, we can add linear combinations of V1 and V2 to get any phase we want within 0 to 2 pi for a cosine. So V3 is simply a cosine of the new phase. So in that respect, it's redundant. The fact that there's a 2 out front is no problem, because we could get that by scaling our linear combinations so that we get that 2 just right. So the question is, are they linear dependent? And the answer is yes. You can go ahead and look at that if you like. In fact, we could show that we have linear dependence for any phase shift. Okay. So on to another fundamental property of linearly dependent sets, and that is, suppose that we have some set v1, v2 up to vn, and they're linearly dependent. Then we know that this exists. We can basically find a set of A's such that the sum is equal to 0. Well, that means that for one of these, for which AK is not 0, and is not equal K, we get this relationship to the rest of them. So we pull out one of the non-zero ones for AK not equal to 0. So linear dependence, by that definition, shows us that anytime we have a set of linearly dependent vectors, we can express one vector in terms of at least one of the vectors in terms of the rest. Without changing the span. And we can repeat until we have a linearly independent set. So, what does this mean? Actually, this is a really good time to... No, actually, we can do this. We can finish this in this one lecture here. And that is, since we can always kind of take a set of linear dependent vectors and consolidate or remove vectors until we are down to a linearly independent set, this suggests that or gives rise to a property that we're going to close out with today, and that is a concept of the minimum number of vectors that we need to span a space. Okay, so right now we're going to stick our discussion, or limit our discussion to finite dimensional vector spaces, and we'll talk about infinite dimensional ones more later. So a basis of a finite dimensional linear vector space, I'm just going to write vector space because it's the same and it saves writing, is a set of vectors B such that 1 the span of B is S, the full space, and 2, B is linearly independent. So this second condition here, we can start with any number of vectors that span B, and we can continue to winnow those down until we have the same number. So the second condition ensures that whatever set of vectors we choose as a basis, each will have the same number of elements. And now you can see why we restricted our discussion to finite dimensional basis. So, given that, we can define the dimension of S is the number of, let's just put this say, elements required in a basis for S. So we're familiar with what happens when you have something like in Rn. It turns out the dimension is n, and the number of basis elements is n, and that's easy to do. But here's one example, and there are a few more in the notes. But let's assume that S is equal to the set of polynomials of degree at most P. Then there could be many bases for these, but one of them is the set 1 t squared all up to t to the p. And so the dimension of S is p plus 1. So this is one of those cases where you might look at it and say, polynomials, they're continuous. It must be infinite. But in this case, no. The dimension is exactly p plus 1. So a nice little finding there. All right, so that's it for this lecture. And talk to you again soon.